Okay, so welcome everyone to this new episode of EagleFly The Experimental Debugger. Today we will continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and be welcome. Um, yeah, you have any questions, post them on Twitter or YouTube and I'll be there to answer, okay? Today we will continue making the disassembler, and yeah, that's where we left off the last day, and that's what we will do today. So let me close all this stuff, and I will open the project. I will compile, and let's open the debugger and see what's going on. I'm sorry. So here we go, and we're running to see where we left off. If I do remember correctly, we were making some compression oriented programming in the last stream. So let's see if we have our stream back. And there you go, we have different the same instructions that we had before, but yeah, we were making just a cleanup in the code so that now, well, I mean, not everything, because I think we didn't finish it, but some of the code now it's already compressed, and it's already getting more tinier, getting tinier here. But yeah, we have a lot of work to do about that. So let's go back into here and continue with that. So let's see. I believe the last thing we did was on the get mnemonic. That was the first indicative of that. Well, that we had that kind of compression thing where instead of having, if you remember here, we have a bunch of code. Now we just have push register name, and that's all we do. In fact, well, that's all we want here. Want to push it, and I'm sorry. Waking up at 4 in the morning, it's a little bit weird, but yeah, it's 4 in the morning, and we are streaming. Well, we're not streaming, but we're recording EagleFly for all you guys in Europe, or in Asia. Probably can be this Well, if we were streaming, of course, but yeah, we are not. So yeah. So yeah, this is the last thing we did. We push register name on different sides here. We push register name on the register operand, and we push register name on the get mnemonic. So that's pretty much it. And we also made this make offset selection mode RAM, which is not the compression by itself, because it's not like we reuse the code, but it was like yeah, because we found out the problem is that the order of the things that we use here are different, because for some of them it's B and then R, and the other is X and then B, so it's not like, oh yeah, I'm gonna use this stuff, we can make it model if that makes sense, just passing the parameters that we need to for the call that we want to. We can try to do that. We can also try to, just because of the order, we can, it's not like it has to be that way, we can make the transformation so that it just matches the fetcher and fill thing. So I think, if you think about it, that's something that we can do, that was something that we were thinking about to do on last streams, that we thought, well, it makes sense that we have X and B in that way, but for the SIB, which is the case. But normally, in the field themselves, because if the semantics are that we are looking for the same fields, then this is not the way to go and look for, So the only thing that we need to do is just to change the data information and say, oh, I'm gonna go and get it from the index or the base, whatever. So let's say that well, let me think about it. Well, we would just need to change the order of it, and over here on the well, let's see. Let me think about that. Here you go. We know that they have the same ordering. We have EAX, CX, EDX, EBX, EBP, ESI, EDI, EX, CS, ESP, EBP, ESI, EDI. So the thing that we need to change, if that's the case, is that it's just the flag, probably. If you go and look for the flag itself, here. Here we use the same flag, and here we lose. Because if you think here, we were just passing the flags, and that's all what we want to do. We want to get to a point where we just pass the flags. We don't want to care about it anymore. So that's our target here. We just pass the flags, pass the flags, pass the flags. And in push register name, we use the flags for. We don't use the flags at all. We don't use the flags. So we just like push with effective operand size, and that's all we do. And we change the offset if we have a U-by there. And we have this selection thing where we select the rect trip and the offset, which that's okay. So yeah, this is just like a special case here. So we don't need the flags. We can just read about it. Compile. We can just read about that. So if we run, if we run this, oh my god. One more time. Everything should be the same. Okay. It looks like yeah. So if that's the case, then we could just continue. So we were like, let's try to think about that. Let's go for the flags. This is the memory operand. This is the other case. Save by the person. Yeah, we have to also think about this one, but where is it? Here you go. If we think about changing this one, the things that we will need to change are rather only change the flag whenever we look for them. Yeah. This on the memory. We set them to true as it basis, and whenever we go for the SIB, we nullify, which that would be nice because we wouldn't need to do this anymore. Yeah, we will still go and look for it. Now the reason is that here we're looking out for the base, and here we're looking at for the index, which is the normal case. So we think of the base as this one, and the index as this one. Now we could think it the other way around and it would be the same, you know? I don't think there's no reason why not to do the other way around. It's just like you have, instead of looking at that's the base as the base, you know, instead of doing this, we can do this. All right. And what we want to do here, we're going to look for the index as we see here. Pass flags, that's okay. We pass the buffer size, the buffer count, the buffer context, and the disassemble state, okay. And here, this is the idea. This was all for the base, especially this one because this is the SIP. Well, all this works with the SIPs. These are the special cases. This follows I32. Reasonable special cases. So we can just get rid about this. And we looked for the SIB by. The SIB by here we're looking for the row. That means that all this stuff has to go outside. And we have another on the ESP as an index, and we have wherever we have the addressing from, it was the same case here. And okay, so this is for the index size. So this could go inside here. And we go and look for the index. And then we can say we will need to, yeah, all the changes that we have to do there is here, you know. So let's do them. So we can just think about it as the base and not as the index, you know, which I think is more correct, or at least that's the way they thought about it. It's just that they changed the way they were explicitly doing it that place. So here we use the base size, and we use the base size as invalid. This is gonna be now effective address size, and this is gonna be data size invalid. And here we're gonna say that displacement is gonna be blah, the base size. Whenever we use index size, we're just gonna change it. Displacement, we're gonna change the use from base size to index size, from index size to base size, sorry. And then there you go. So let me go and find index size. Here you go. This is correct. This is the index size. And here we're looking for the index size. Now, how do we know that we are looking for the index size? Well, we have to look for both, isn't it? We have to look for the base, and we have to look for the index. So we have to think about the size of it. And here is the place where you have to think. Here we go. I can do it that way. Oh, and I see the problem. Yeah, because since well, the only thing that we need to do, of course, is just to do this. Yeah, the order will need to change in that case, because now the SIB goes in here. And then we always will have a base, you know, that's the first thing we go forwards. Then we try to find an index scale. If we don't push anything. And flag member fields, SIB fields, get SIB by fields. We can just this here. While we were doing this, okay. Okay, so this is inside the SIB by thing. So let me think about this. This is for displacement equal data size 32. This is for the special case that we have here for the SIB byte, that we have a displacement 32, that in other cases would be nullified. Let me put the charger. So let's think about that. So the only thing we need to change here is just that, yeah, this thing right here is for the SIB itself. It's just that it's just this special case where we have to think about the displacement. Now, the reason why do we have to nullify the displacement in that case, it's something to think about, because it was here on the mod that we make the first check, and it's like this is 32-bit. If the RM field equal to 0x5 and the base size is going to be invalid, otherwise the displacement is going to be data size invalid. Okay, if the case is that we have 1, the displacement equal data size 8-bit, or if we have 2, the displacement is going to be data size 32-bit. That's that makes sense. I mean, that's normal. And the base, we haven't looked for the base here, so we have to think. I'm gonna move this a little bit, and I'm gonna put it here somewhere on the place we had it before, and I'm gonna erase this. Don't need that. I'm gonna put this. We can in fact do this. Yeah, we can do this inside here. Yeah. Just like the SIB checker, and but we don't need that, but we just need to think. So we have these two, and then in this case we're not gonna add anything because we don't need this, so we just do that, and yeah, that's all we need, isn't it? And then this is if the index size, now it's gonna be the base size, blah blah blah. We're gonna push a plus in there, and then if we I mean, probably this is not gonna stay in the future. This is just a way that we find out that it was simple to do this. But yeah, I mean, the data composition for the operands probably is gonna be something that we have a little bit more of thinking of how do we want to do that, but for now that works. Okay, hold me a second. So yeah, so index size here, no index size, just space size. Okay, that's good. I like that. Let's be by person. Now we can do something about this thing, this weirdness thing here. So yeah, this will change the displacement. This will change the displacement as well. There's an extension, it's all about this, and the push string that we close up. So this is just an extending here, yeah. And here this is just looking for the size explicitly, yeah. For all the types, the size is extending and filling up the gaps with the right values inside the stream. Pretty straightforward. This is okay, I like that. And then here have if we're looking for the SIB by and how much the displacement should look for, you know, that's alright, I guess. So let me go first and solve this transformation that we made here. Okay, so whenever we go and fetch for the base, is because we put it here, yeah. If I move this here, sense because on the SIB fields on the base we have 0x5 and the math equals 0x0. That means that we have a data size 32. That's because this one. So yeah, we have 5 and the math 0, and we have displacement 32. The other cases will get matched, you know, because that's the normal thing that happens. This is just an override that happens, and we don't fetch the base register. That's pretty much makes sense. So this is important. So I like this because now this is more compact in the sense that okay, we have SIB, we do the SIB thing. If we don't have it, we do just the base stuff, you know, just base plus a displacement. That's all we do. And this is can be like, okay, we go and fetch for the base. We can override with with their own stuff, you know, that the SIB has its own rules. So these are the rules for it. We just make the change there, and we go and fetch the base register as it is, you know, with the own flags. And then here, this is, well, index size is already, it has to be defined somewhere, and it's here with the effective address size. So it's just, if we have this thing, is that it's gonna be invalid. So yeah, this was like that. That's okay. So we put a plus there, and then we look and fetch for the register operand, and then we go and look for the index size. That's okay. And then if we have a possible index size and we have a scale, where do we find out that we have a scale? It's on the SIB by person. Okay. Okay, it's kind of interesting. Yeah, I guess it's just something that we have it. I can defer it here, you know, so that if we think that it's just like the thing we have here. I mean, there's no reason why not to do that. Right now we don't use that. So we can just say you can do it this way. And we already have the SIB bias, so we don't care about that. Have the SIB bang. We don't have to do it twice there. And we have a symbol. It's okay. And this is gonna be we shift by 6, we get the scale, and then we just mask it out. And then we shift by 1. Whoa. What are we doing here? Oh, it's because we are thinking about we have to shift 1 by an offset. So yeah, we use that as an offset. So if the value is 0, we shift it by 0. That means the scale is 1. Shift to 2. Yeah, that's correct. So yeah, this is correct. Okay, so we have this core temp. It's just temporary push string, temp count, and we can compress this stuff. You can use it as well. I just first want to make the transformation so we can just make the compression on the other side, and then we will continue with other compressions. Okay, so let me do them. Okay, so yeah, I mean, I think this is the same. Now scale is just gonna be a unit 32 thing, and normally we don't need to think about scale here. Well, yeah. It's just gonna be times 1, so yeah, I mean, we can do that later, it doesn't matter. And then we can just do this in line, which is better. And then we push straight to the buffer. There we go. That is the symbol itself, and then we push string to the buffer with the temp B, which is the scale. Alright. Yeah. Well, that's okay. Yeah, so let's compile that. Let's solve for the errors. We don't need this anymore. And Okay. So we have a scalar. It's just that we pass it out. Yeah. I mean, normally the scale is not gonna be a thing unless we have the SIP. So yeah, I mean this is now something that just like that. There you go. A simple transformation there. So that we can just make the change there. So if we run it right now, it's just gonna be bananas, you know? It's gonna be bananas. In fact, if we try to match it with the real thing, probably we're gonna find out some surprises. Have push R12, push RVX, move SPL RVX, move RVX R13. There you go. We don't have the R13 here. RVX times 2, RVX, RVP. We don't have RVP. We have RVX. We just have REX everywhere. Okay. We have RVP. We don't have RVP there. REX times 4. That's correct. RVX, SPL, RVP, RSP. Here it's another problem there. FF. The displacements are correct. That's correct. We didn't change that at all. And then we can just do it that way. And then R8, R for equal pointer, R12. And it's thinking that we are doing RSP. So yeah, the REX prefixes are just busted. We have R13, then we have R14, yeah. So yeah, I mean it's just all busted, okay. So yeah, we have to change that. XML0 REX F0 OP REX RDX. That's correct. Okay. So yeah, I mean that's what we were expecting. All bananas. And the reason is because we haven't changed the thing to be that case. So now we think about the base and we think about the base itself, you know. So let's go and change that in the same place that we're doing before. So the index size, normally we have the base size here, and then we have the index size as well, or then we have the base size here, you know. And here we have the model by false, SIB by person, true. Now this is something that we have to think about. That's okay. Index size, SIB byte. And then So if we do that way, let's go to fetch register open, and since now we're not changing at all, we change the idea that we have a base now that we care about. We can just uncompress this stuff. What is it? And say that we have before the model RAM thing. This is correct. Whenever we go and fetch the model RAM, we have BR. That's the way it is. This is okay. And then whenever we fetch with the SIB, this is where we're gonna need to change, and this is gonna be B, and this is X. And then this is well, this is the base, isn't it? It's gonna be the same, I guess. this won't change anything, isn't it? But let me see what we did here. Oh, okay, yeah. So we're missing something here. The flags have to change, if that makes sense. If we are going to look for the base first, well, we have to do it that way, yeah. And then we go and look for the index, and then we just look for this. So flags first is going to be the same. Fetcher and fill is correct, and here is our fill. So now we got the X and we got the index. Does that make sense? I mean, it's pretty much the same. It's just that we're looking at differently. So if I say then we are going to see that we have R12, REX. Well, let's compare it. We have, oh my god, what happened? R12, REX, SPL, REX, RBX, R14, REX times 2, RBX, RBP, REX times 2, RBX, RBP plus REX times 1, FFFFFF, RBX, REX times 4 plus 0.003331100. Then we have RBP, RSP plus R12 times A plus 0.03321, R8 plus R12, sorry, R12 memory address. and R8 R13 plus 0 0 0 R8 RAX plus 0 0 3 2 2 2 1 1 0 0 RAD RAX 0 0 0 3 2 2 2 2 2 1 1 0 0 RAX RDX at RAX plus FFF0 0B F add ST0 ST1 FUCOM ST1 ST0 FLD it's 04 VM resume PLNR XMM0 XMM1 08 shift left double displacement EAX03 add EAX throw pointer 00. Alright. So that's correct. That's good. That's good. That well the only reason that we and now that we do that, we have a match here, probably it's just that we have the difference on the REX itself, but now we can make a compression, now we can just make the compression and say that here make offset selection I'm gonna do that. I'm gonna compress all because the compression that we made, it didn't work. And this is what we had the first time, well, the other way around, but now if we compile them, it should be possible to get the same thing. So this is selection, so if I run this again, no change at all, we just uncompress it, okay? And there will be no problem, it seems fine. So now that we do that, now let's make the real compression, okay? So we're gonna do that, and then if you see here, we have now the same order that we wanted. We have the same base. So what we can do is just say make offset selection, and we pass the value that we want. And then we pass the selection as it is to be modified. Do we need the context? Probably not. We can just do this. at the first time. I can just move this here. And I can just uncompress that. This is the only thing that it needs to change. I will need to push this stuff here. There we go. And we will need REX, and in this case the only thing that changes is if we got here, we need to choose the proper value. We need to think about, well, that's the only thing. I mean, that was the only problem before, you know, like, oh, we need to use this or we need to use that. And of course, do we need the context? No, we don't. Do we need the flags? Yes, we do. I'm gonna pass here. We can do that, and the other stuff would be the same. Okay, let's compile that. This one need to do it like this again. and this now can be this pass the session state, pass the decoder context, pass the selection, it's an address, pass A, we pass B, so we pass RM, and then we pass the rec, and then we pass the flags. There we go. Yeah, I mean, the only thing that I don't like about that compression is that it just hides the selection, you know. It's just like less clear that which one. I mean, since we're passing the parameters, it's just a little bit weird. But I mean, if we can find a way not to pass it, probably, yeah. But well, I'm gonna leave it like that, I guess. Doesn't matter. And this will be the same. It's just that pass the base first and the index next. Okay. Then we can make the compression again. Yeah. And now we could be hoping that it's just gonna be the same thing. And this is because we have to think about this. There you go, there you go, okay. So let's see what happens now. Who knows what's gonna happen? Who knows? And we have that output, so let's make the comparison. R12, REX, SPL, REX, RBX, R13, REX times 2 plus displacement, RBX, RBP, REX times 2 plus displacement, RBX, RBP, REX times 1 plus F RBX, REX times 4 plus displacement, RBP, RSP plus R12 times 8 plus 0.0322110, R8 core pointer, R12, R8, R13 plus 0.000, REX plus 0.322111111. Yeah, that's correct. REX RDX, REX FFF0 OP, F adds to 0 is to 1, S to 1 is to 0, and FLD 0004. Let me just join this together. FLD, yeah, the Vim resume, P line R, the shield, and the EAX. So yeah, everything is the same. Everything is the same. So now the compression is effectively done there. We just needed to do a little bit more work to make it happen, but that's it. As such, now we have compressed this, you know, we can just do the same thing with well, I think this is okay. I mean, it has the basic idea. So let's go to the other side. That since we already moved for the fetch mode around, let me go fetch memory operand. On the fetcher memory operand thing, now we have a nice thing about compression, because you see here we still have to push some stuff, you know. Now this looks it looks good, you know. It's a very compressed bunch of stuff that we had before. I put it through here. Well, we could make the choose not to do it, isn't it? I mean, what we can do instead of passing rm rec, yeah, we can do that. Yeah, let's make that compression as well, you know? Because if you see here, I mean, this is the same, you know. I mean, we make the exact same shifts and we make the exact same information. Of course, they are passed a little bit differently, but we can make that also a thing. And then we just don't need to care at all, you know. We don't need to care at all. So, for example, let me go to make offset selection, and we will need only to have this thing, something like that. And here we just pass the value, of course. And then we just don't need to do this right here, and we do it here. You know what I mean. And then here is just value, and then here is just the thing that we need to fetch out. First we have 3.0 and then goes rec flags. So it goes this way, okay? Rec, and here goes this way. Base index. So yeah, they have the same order, isn't it? So we just need to do this and say A, B, and then we just A, B. That's it, isn't it? Let me think about that. Yeah. We have 0, 3, 0, 3, base index, rm rec. That's all, isn't it? So if we do that thing, then bye-bye. Bye-bye. So we just need to do that. And here, of course, we'll just need to do this. Well, in fact, let's just inline it. Okay? There you go. We just don't need to do that all. And this is the model run by. In fact, yeah. That's all we need. That's all we need. Yeah. And now we just make offset selection. And that's all we need. And now we can just make another compression. Because in fact we don't need to call it twice here, you know. But let me just compile. First, we don't need to pass this at all anymore, nor this anymore, and we have to call this properly. Just continue with this. There you go. There you go, there you go, there you go. So let's see what happens now. One step at a time, we see what happens with the compression. R12, REX, again, one more time. Oh my god. There you go. Oh my god. Push R12, push REX, move SPL, REX R13, REX times 2, RVP, REX times 4, SPR 12 times 8, R8 to 12 for 13, R8, R8, REX times 4. Hold on a second, where I am. Oh, okay. So my bad. RAD, REX, REX, RDX, REX FFF0, ST0, ST1, ST1, ST0, FLD04, BM resume, PLINR, XMM0, XMM1, OH, shield left double, EAX03, and at EAX. So yeah, we have the same now. Some compression there, some good compression going on there. And now we want to go a little bit one step further. We just don't need to do this like this, and we just make the selection by our own. We just say, well, you know, the value that we want to have, it's a modern bind. I'm gonna call it input. Input call it byte or whatever. But it's gonna be 0. It's gonna be like this. Yeah, and this is like this, and that's all she says. If we make the compression, then we make the compression. Oh, and this is the byte. Again, same thing, compression, 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 compression. We can just do that, and there you go. The same thing, same stuff, just compressing it, following the right rules. Okay, now, yeah, I like that. And you see here now we just have this little call here. Right now we cannot compress this. Let me see what else can we compress here, because if we can just compress it to the limit, we can just try it out this one. This needs the fetcher and fill as well. Right now we don't know. Yeah, we have put to do here because find out, make x87 encoding properly. So we have still, we cannot compress it right now because we are not doing it in the way that we wanted to do in the future, so I'm gonna leave it that way for now, but the offset selection is pretty nice. It just has that utility that you can just go and look for which one we want, and that's all we want to do, because that's all we want to do. We just want to get the correct byte and give it to it and return us the selection. A nice call there. And yeah, and then we just push the register with the selection that he gave us to us. We just assert that the selection is valid. It's correct. That makes sense. And that's it. We can just make rid of this, but yeah, in the build, when we compile for release, it's just gonna be off. So yeah, then results go true, and that's it. That's all we do there. So that's nice. So now let's go a step further here and make more compressions. I'm gonna leave this like that. I guess it's just the way it goes. We can get rid about all this stuff probably, but I'm gonna leave it like that right now. Now we don't need the info here anymore. That's good. The selection is not needed. Oh yes, it is. And now, I mean, it's, you see here, I mean, it's just easier for us to think about this call, you know. So you just make the object selection and we push the register name. That's all we care. We just find out from, we just have the thing, oh, mother m by +1, that's good. And that's all. So now let's go, yeah, I mean, I think that's, I mean, I feel, I make the feeling about it and it just feels good. Yeah. Okay. So now that we do that, we can just continue with this. So let me go to fetch memory open and see what we can compress here, okay? So it's just gonna do the same stuff, you know. We need to have a fetch register operand that overrides the operand size for the 50 operand size that we wanted to. That's good. Okay. We have data size invalid. Data size is the displacement stuff. Push string. So we have special casing here. Check it, do it, go and look it for. We have the same call here. The fetcher and fill is not used, but here whenever we go and change for the base, for the index, sorry, and that's it. We don't need it anymore. We just set it to true at the first bar and we set it to false here. And what about this SIB by person? The SIB we set it true. We need it just to make the displacement fixed, you know, to path the displacement to the proper place. Yeah, I guess it's good. We could think about we could think it as an offset if we wanted to, but it's just gonna be the same, I guess. Well, we can have a call here, you know, like So here we're just like making the offset. And here we're finding the offset, okay? So we can just say make it can be displacement offset. And that's all she said. It's gonna be the same, I guess. We can call it yeah, it's the displacement offset from the mother end body. That makes sense. Yeah. Can make define here. And well, that's the first thing we can do. The strings, yeah, I mean we are using it both. We have temp count here and temp count here, so we can just have its own pushing if we wanted to, because we have to convert this. I don't know if we want to compress that right now, because I mean we are not gonna keep this at all, you know. We're gonna make our own spring def whenever we need to, you know. But yeah, I'm sorry. In the future probably we're gonna make this change. So we make the solution for this scale, and that's all we need, and we push it. We push that value, and then we push thing here, it's the same. Push string here is the same. symbol string length. So yeah. So yeah. So I mean, well, this is not a lot of things repeating themselves, so it's not like there's something visible that we can compress right away, but we can just say well, I mean, the nice thing about the movement that we made here so that the other compression could make happen is that now we have this, it's better, in the way that we represent it, because we have SIB, we do the thing for SIB. If we don't have SIB, we do it for model RAM, and then the displacement is just its work, So that's it, So we have the pieces that in any cases we will need to make any more usability. Now everything has its own semantics, We have first fetcher, first SIB, then displacement, First SIB or normal base, and the displacement, and that's it, We don't need anything else. So for that case, it's just good, The order is correct, and first of all, we find out with the flags if we need anything about it, We modify the displacement based upon that, and that's it. And here, now the thing I would like to think about now, it's these offsets, because right now they are just playing around, like no caring at all about how they should be done, So we wanna correct that and have a proper way to modify them, not just having them all around movement. Because if you see here, I mean, they don't have an order at all. They just are put in line there whenever they were needed to. For example, this one, why is it there? Or it's not like super understandable why do we have the offsets like that. So I think that's the next thing to think. Now that we have the calls constructed in the way that we wanted it to, we just want to make the next thing to do, which is solving the offsets. So let's do that. And if you remember, for the offset stuff, we have a nice thing to do. I mean, we solve our problem for ourselves, because now the offset, it encompasses the whole instruction, which is nice. I mean, it's what we wanted, because before, if you remember, before having this call like this, we have a crazy stuff happening there, like this was independent, this was not on the same frame stack checking, because we didn't have the context being made properly. So now that we have a context, then the context is the one in charge of having that counter. It's like, oh, how many things. And in fact, if you remember, we have here in the context, we have the fetch count. Well, it's no, the operand offset. So this is the operand offset, and it's not operand offset. It's just that I'm gonna call it instruction count, instruction length, instruction count, instruction length, and instruction length. And we can just make rid of this. There we go. I'm gonna call this like that, and yeah. So let's think about this for a moment. I just modified it so I can see all the places where we have the lengths and the context make them, so we can just start to move them around. So the first place we see the problem is on the fetch register open. So if we think about it, I'm gonna move on the here. So every time we initialize the context over here, the context is null. That means that we have an offset of 0 and a fetch count of 0. That's correct. That's the normal thing. And then we just start moving this, context CBY, and we can have this thing here being moved from the prefix itself, so that we just have instruction, and probably that in the future is gonna work a little bit better if we wanted to yeah, probably that's what we want. Even though right now, probably in the future, well, I'm guessing here, yeah, and probably that's not good. But I mean, in any cases, we need a pointer to the base of the instruction. In any case, we wanna keep right now we don't print RIPs, but we wanna keep the RIP correct. So whenever we move to the next RIP, we know how many we have moved around. I mean, that's not probably the problem here, because it's just that whenever we finish up with the CBY, we know that onto here we have CBY on the next instruction, so we just print the instruction offset. We can just compute it that way. But in the sense of order, in the way that we want to, we just want to have here, instead of this, we just want to have we don't want to move the byte until, this byte should not be moved, it's like having this, because right now we just we don't have an order. We found the order that we wanted, we need the byte right now here, we need the byte right now here, we need the byte, probably we want that still, but we want a base, instruction base. and then the byte, and then the rex byte, and then the up count, and then the thing. And that's gonna be good, so that we have instead of having this, you just have instruction base instruction length, and that's it. So that's what we are looking for. And then we don't need to serve by that. We can assert the instruction base, let's say. But that's what we're looking for, you know, something more like that, so that the semantics start to encompass the instruction itself and not just like a bit field, which is not, I mean, it was good for starters, but we have to start thinking about the whole bunch of places, because in the future we are not just going to have one instruction stream, but probably many instruction streams. Probably we have many segments, and if we want to make a proper ordering of instructions, we still will need the base. Okay, so let's make that transformation, you know, so that we use the base now instead of the weird cby thing that we were just moving around. Okay, so we did that. I will compile, and the first thing, I would like to go to get mnemonic, because this is the first place we move it. So context cby table modern by. So the table ID returns this table that has by itself the place where the modern byte is. So I'm gonna make these offsets now, you know, it's the first change I want to do, so that we always have all relative to the instruction base. In that sense, we don't have to think or guess where the modern byte is, or if we have any problems about the file, you know, we just have an offset and that's it. So I'm gonna call this offset at what was it, offset modern offset, and this at mod at offset is a place where we want to move. Let me think about this first. So it's normally is 1 byte or more, the modern byte, and the at, so it's probably main of byte. Let's call it main of byte, main of offset, modern offset stuff. Okay, That's all we want to do first. So let's compile, and let's change this to main offset. No, main offset. Compile, and this is gonna be this. There we go. There you go. And I'm just gonna do the cleanup here, okay? I'm gonna buy, then there we go. Then we have BX, we don't care about BX. Care about that. I don't know why do we have this one, but this is like this. Whatever. Making this simple transformation. And what are we doing here? We change the table ID. Alright, this is gonna be and this is gonna be there. And now the only thing we have to care about now is to move the instruction lane. It's gonna be context instruction. And we can, well, we'll need to do it here. We can do it on the upper side. We just need the offsets. That's all we care about. So the offset, yeah, the offsets, and yeah, that's it. And I can solve this 0, 1, 2 thing, so that instead of having all this, since I don't know why we didn't do this first. Well, on the how can I say it? Whenever we started doing this, instead of having all that crazy stuff of the referencing, so we can just say unit 3, unit 8, first byte, well, first byte, second byte, third byte, and that's it. And we just say first byte equals second byte equals third byte equals, and then we just say, hey, you know what, well now think about it. This is gonna be first byte, it's gonna be this, second byte, third byte is gonna be this, and I think that's all we need, isn't it? And then we just say, well, you know what I mean, first byte, and then I'm gonna change all the main of bytes for first bytes, okay? So whatever we see this, I'm gonna change it for this. Oh, and I forget. I make the wrong key code. Okay, so main of byte plus 0, separate. Yeah, I'm gonna change it to first byte. Right? Boom, 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 boom. There you go. I'm gonna call this first byte, and I'm gonna call, yeah, and then I'm gonna change main of byte plus 2 plus 1. We have main of byte, no, main of byte plus 1 to second byte. There you go. There you go. And now it looks much better now. Well, second byte, this is third byte, and oh, okay, I see why I was doing that. Okay, yeah, do we use main of byte plus 2? Main of byte plus 2, do we use this one? We're not using it. We have, it's because we have OF create. Oh, okay. And this is, for example, the 3 byte thing. Main of offset is 2 and the mother n byte is 3. We already know it because we just need to check the first 2 bytes for now, because we don't check EBX prefixes, so that's why. But in the future we're gonna need it, you know. So yeah, right now we don't need it, but yeah, I'm gonna keep it that way. And yeah, so this is gonna be called mother and offset now. There you go. And then we can just return the result. Okay, let's compile. I want to go to get mnemonic. Oh, here we go. And since we fetch eraser, well, no, yeah. So now we've got the offsets here. So now we have to change this now. So we have the offsets from the table. why do we call it table? It's just like I don't like that. Yeah, I mean, we have a table ID, of course, and the offset for the consequential thing that we want to do with them. That's nice, of course, but well, yeah, it's okay. It's just a little bit weird. So we have table, and then we're gonna main up. This is gonna be main up offset. So this is gonna be this is gonna be context instruction base. I'm gonna call it ibase. Ibase table main of offset, blah 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 blah, and there you go. There you go. And then ibase ilang. There you go. Yeah. Hold me a second there. So we got the base and the main up offset, and then here we get the right one from the alt table entries. Oh, we get the entry index. Okay. So we get the entry index, which well, I don't know why we don't do that like that. And then I don't know what to. Okay, I'm gonna leave that the way. And then we get the entry. I mean, this is the whole thing, This is the right thing. Get mnemonic entry. This is the whole thing that he needs to do. And this is just the extra stuff about if we have an entry, an operand inside the main byte, which is in this case, we just push the RxB. If RxB selection group as a strip, okay. That's okay. And we could still compress this thing with the, if you remember, the make offset selection. We have REXP field. We just have to pass the thing that we want to do and the selection offset, because we still have a selection offset. The selection offset is context byte and 07. Why we were doing it? So I'm gonna call it this one. Now it's gonna be static, okay? Table main of offset, context side base, table main of, okay. To this base frame, okay? I'm gonna change the C byte. I'm gonna say that we're gonna have this unique D pointer context, well, C byte, and then we do this, and then we can just do this. Now I don't know, well, 0x7 is gonna take the first 3 bits, and that's okay, I got you. I was like, what? Yeah, probably offset. Yeah, because now we are like thinking about offsets, and yeah, probably this is gonna be called different. And right now I'm gonna leave it that way, but yeah, we have to change that. Input. Change this name to values or something. Value to be compared, whatever, to other thing. Not offset. And erase open size, open mode. Yeah, raise to open size equals to that thing. Well, yeah, I'm gonna leave it that way because it's just totally different. We're not doing that thing here, yeah. In fact, well, we can do it if we pass it as an A and REXB shifted by 0. We can do it. We're not gonna get B, of course, but that's because we are looking for fetcher and fill. We just need to pass the right thing here. So yeah, well, it was probably something good to do. So we just need to think here. You can pass this and stay context. The value is gonna be something selection. I'm gonna pass it as well, and we're gonna pass the flags as well. Pass flags, okay, and that's it, isn't it? So here we'll need just to say with the flags fetch or fill equal true. And that's it, isn't it? So let me just do it that way. So I'm going to leave it that way. Here we have value. So we can just say that we pass it here. There you go. We don't need this anymore. And well, right now, well, I'm gonna take that out. And then Well, I'm gonna do that. More compression oriented programming happening here. And that's all she said. Yeah, well, probably it's gonna be faster if we do it the other way. But I don't think, because there's less instructions to run, but I think that's nice. At least semantically. I think there's gonna be a lot. I don't think it's gonna be a lot of problem of that extra instructions to that. If we wanna that we run each time we get the mnemonic entry. Of course, yeah, get the mnemonic entry is something that has to be happening a lot of time in the loop, but and if we want to optimize it, probably it would be nice. But yeah, I don't think that's the problem. We just have to fetch RM field. Normally, when we go and pass the get mnemonic entry, I mean, the flags themselves are not looking forward to that. So yeah, I like that. Yeah, it has to be that. Yeah. So that's pretty much for it. And then we can just say that we have instruction island equal to table modern. Mm, mm. So I don't know if you probably still want to have something like this, where we have the begin stuff and end, which probably is nice, you know, begin that we already solve it. We erase it. Begin instruction, decoding. Probably, yeah. So that the island, it's just being passed every time. So we don't do this because we don't want to modify the length up to the last part. Probably we want to have an offset and the base all the time based, you know, like, oh, you have an effect, you can do this, you know. So all happens in the context of it. Yeah, why not? And then we can just make some compression with this stuff. Begin instruction decoding, that's okay. And then we end instruction decoding. So let's do that, you know. So for starters, we will do this. And just say then or yeah. So we just do that. And what we do here is that we say we can just make an insertion, the same thing we did before, context space, and in fact we can just say the I mean we just need to do this. Just do that. So let me copy the whole thing here. And in fact we just can't do this. That's all we need. And here we say this, of course, and we say different stuff, of course. Assert island. I'll call it island, yeah. And what else do we have here? So that we say ibase plus island is so. Now we pass it here. Yeah, I think that's it. And in that way, it's super simple. We just have to move it every time. And that's it. Yeah. So what about that? Okay, so now that we have that, I know we still want to have a cbyte. I don't know. So we can just do that for now. We can just stop it. I'm gonna do that so we can see as well. Fetch register open. So we're on the mnemonic first. Where's the mnemonic? Here's the mnemonic. And if that's the case, we just have to count it, you know. So the up count, well, where is it? Island, ibase. And we want to have this by count. I'm gonna prefer this than this, yeah. I'm gonna do that. And then do that. This is that. This is like that. This is like that. Okay. So here I'm gonna say by count plus equal table model variable offset alright, that's good. And this is just the same, so that's good. And then if we pass on to compile, then we go for the fetch register open. Before doing this one, I want to go to the other fetch register open, or we can go to the fetch memory open. Yeah, because that's the next one, isn't it? Fetch memory open. and we have here an upper and offset. We call it upper and offset because it was upper and offset, but I'm gonna call it by count. There we go. And then, and in fact, well, I can call it here as well. Well, I'm gonna leave it that way because let's go function by function. So by count this, that's good. So for example, whenever we move this by count, it's because we're moving it from here. So we want to have this fetch register operand doesn't modify the by count, it just modifies the counter. And that's correct because yeah, the weird part about this is that we have to fetch in the same byte we have to fetch on the same byte the mod and the rm. That's the reason why we don't move it here. Shall we make something more clever? Yeah, we have to do something more clever here. I'm gonna say count for now. And maybe then I'm gonna move this here. And then I'm gonna do again fetch memory operand. So we're gonna have a backend. At first we got the entry, that's okay. Got the buffer, mother and person, context c byte, and this is gonna be different now. Context I base plus context by count. If you think about it, I mean, it looks more complex, but I prefer it that way because it's easier to think instead of just like trying to think about where's the byte or something. Now we can just say, hey, you know, how many bytes have we passed from the base? And with, I mean, that it's more. It has more sense, you know. That's what we say. It's just like we have a base. That base never is gonna change. You know, the byte count is the only thing that we're just like moving step forwards every time. And you know, we have the context, byte count. You know, whatever we move it, and we have a byte count. And if that's the case, now I don't know why we have this byte count, because what will happen, I mean, probably this is okay, but in the way that we have the order, we first fetch the memory and then fetch the register. Alright, so and since the register, probably we want to do it the other way around. You know what I mean? It doesn't matter how we do it, it's just the same. It should be the same. So right here on the bottom, we can just say this, and it will be unconsequential, you know. It should, at least. So the problem here is just, and probably it's better because of the SIB thing stuff. Since we are doing it inline here, I mean, we're just going and fetching. We can just have another pass here where we say, oh, you know, we have SIB, which I don't care. I don't think it's a thing, you know. But the offsets care about that, you know, because if we're going for the SIB, then we need the model ramp plus the displacement, you know, and then we go and fetch the immediate, you know, when we may pass by that. So in any other case, we then shouldn't move the byte offset, the byte count. Does that make sense? From this until we have make sure that we have fetched the stuff, you know. So it's even like if we have, since we have a context, we don't even need to care about this here, you know. We don't need to have byte count being moved here. Yeah, we don't need to do this anymore. And well, that doesn't matter. The fetch count, yeah, we're gonna leave that for now. We care just about the, well, I'm gonna call it up count. And SIB by prison. This is the byte count. So it's even more like, it's because sometimes, well, yeah, we can do it like this. If we want to do it this independently, so we don't care about if we fetch the register in the memory, I think that's nice because it's just like the user can put it whenever they want. The only thing that we should care is that the immediate, you know. It's about the immediate. So we can just say we have to fetch the immediate every time. I mean, if we do something like this, where we say context byte count plus equal byte count. Now the problem is that we cannot do here because yeah, we need another variable. We're gonna do it. I'm gonna leave it that way. The thing is that we cannot modify the length. Let me on the first one. So we want to have so this. That's it. That's it. So that we just keep moving, and then we can do the thing that we want. Context buffer count, no, high score by count plus equal by count. In fact, this shouldn't be here, but here. And then what we have, displacement plus displacement offset. Let's have a prism. Which is the case. And that's it. Now it could be the case, well, that we don't have a mother M, but just the rec. And let me remember that problem. It was because, let me remember. I mean, if you remember, we have this one, and we modify the background, well, because we wanna. And I remember why we were modifying the background here, and this is why I wanna get rid of this. We don't need it. The problem is that, what if we have a mother M, but we don't have, and we have a rec field? That means that we are going for this one. But we don't have a mother M field, No, okay, no, my bad. No, because this is always getting for the mod RAM, it's always getting for the mod RAM. So it's just like, oh, okay, we have a byte count. Yes, that's the way to go. That makes sense. We don't want to get modified here, because fetch register operand, move it there in the outside. Oh, okay, I see where it's going. Yeah, I mean, it makes sense now I think about it. I was just like a little bit rigid, but it makes sense since this call, it's been called a lot of times, it's a little bit weird. It would be hard for us to think of this call. Let me show you. I mean, fetch register operand is something that we use a lot of times, I mean, the stack just happens a lot of times. So we cannot modify here the byte count, because it would be nonsense, We cannot modify it on neither of these two, because these calls are just super crazy, Well, not super crazy, but the way we are using it is that since they are compressed and they are used a lot of times, it's just not the place to go. So that's why on the memory operand we just do the whole stuff, because we know that the memory operand is just gonna be called once, and that's the reason why we modify the byte count here. Okay, I see the problem. So yeah, so if that is the case, we can just continue doing that thing, and that's all we do. So we can just say, well, yeah, we have it the way we had it before, and then we can just say that byte count is that, and then here we just say context byte count equal to the byte count. This is equals, and that makes sense. You know, you have a rect, then we don't have a displacement plus that stuff, whatever, and that's it. And then the byte count, we just move it by that, which I think it's nice. And then yeah, the others are not gonna do anything about that, you know. And let me see if we got it right there, because the byte count is gonna move from the mother RAM, you know, or the SIB, which is 2 or 1. This is, I'm gonna call this operand byte count. Yeah. Then more by operand byte count. There you go. And well, in fact, we can just say this. Operand byte count. And this is just operand byte count. Well, if that's the case, now we don't need this anymore. It was good, but yeah, this is better. Here. And then we just do that. There you go. And so this has to be moved here. Uh, oh, okay, so that was the reason why it was working, because we just care about moving one past the operand count. yeah, since we don't need the C byte on the other power, you know. Yeah. So we just need byte count, you know, and here we just gonna do C byte, no, sorry, byte count. There we go. And then the other thing is the same. And do, oh yeah, and here we're gonna say, so we're using the C byte here. So we want to keep that context. In fact, I don't know why we were doing this one, but I'm gonna pass it here. And if that's the case, then that's fine. Well, I don't know. I mean, we can just return the motherland byte from here. It would be good. And then we pass it, and then we move it. But yeah, I mean, this is the hard part. Like, how to move the byte. I mean, in the way we were doing it, now that I think about it, it just was reasonable. It was not anything weird. It's just like we didn't realize that that was the way to go, you know. So yeah, I mean, I prefer the context side because passing the mod range by all the places, so it's gonna be crazy. So I'm gonna move back here. Where is it? Mod range by. Don't care. I don't care about the mod range by. There you go. I need that. So if that's the case, yeah, we need the C byte. We can context I base plus context by count. And if that's the case, And that's it. That's all we do care about. And here we just do that. So compile, and here we're gonna say that we are gonna use context I I'm gonna say that. All right. In that case, then you pass the C by, you know, it's just the same thing here. I'm gonna use that, and then we need the C byte here. So I'm gonna do it this way instead. That way. Context type base table minimum offset. I'm gonna take that out. And this needs to set the reference, I guess. And then here, immediate operam. We don't have a C byte. Oh, this is immediate. Okay. So here we have the thing. Well, it's just that context I base by count, the same thing. And here is the count, and this is by count. That's it. And then the base is gonna be C byte. Okay. So it's just like this. Here we don't have that, and we don't have that, so that's important. Now probably REX bytes just better in this case to be a value. What is it? You can just say, hey, you know, whatever. Well, and probably I just want to do that afterwards. So I'm gonna keep it like that for a second just to finish this. Context cby. This is cby, and then the same. And then I'll need that. Just need that. Instruction encoding, yeah. Well, probably was the same, but by count. So there you go. So yeah. yeah. I mean, the way we're doing it, that makes sense. So yep. Yeah, I like that. So now that we have that way, we can just pretty much run it, isn't it? I don't know if we need something else here. We need to set, we already set the base, you know, and get the mnemonic entry needs to have a byte count properly, you know. So this is the problem. We have to say the byte count properly here. So this is context byte count. And the same here. And the same. And the same. There. So yeah, I mean, REX prefixes is something that we still have to do, but at least we have now the context being properly padded. Now here, of course, it's going to be different. Context base, context by count, by base. And now this is gonna be weird because this is not correct. So it has to be the same. So yeah, this is the only weird part, but for now it's gonna be okay. We don't need to think it too loudly. So I'm gonna change context to context. So let's see with all that changes. I mean, that was not a compression at all, but that was something that we wanted to do to clean up the thing. Unfortunately, we found out that it was not possible to make the thing that we probably want to do. It was like each call has its own movement of the fetcher of the bytecount, but that's alright because we don't have to, every time we go and move past by, we just move it every time. So right now, yeah, that means that the dependence here on the, just before running, I just want to explain. So that means that we have a dependence on these two calls, because if we move fetch, I mean, every time this is the one that has precedence in the controlling part of the memory operand, and that's important because register operand needs of the whatever it passes, so that's why we are choosing it first, and then we'll go and move that so that it immediately has the right byte count, if that makes sense. So yeah, I mean, that's the only thing that we have to do so that works. So if we run this, probably it's going to do bananas. And yeah, it did bananas. So let's see what happened. Okay, let's go one by one. We have C byte. Now oh, we don't pass it, isn't it? C byte. What? Okay, that's for stutters. So the byte count didn't move. The byte count didn't move on the first one. That's interesting. That's probably because on the get mnemonic entry, we don't get it. Well, here it should, because it should default to the 1 byte table, so it's 1 unless we don't modify it here. Which we do. Here we have it. So there you go. So let's run step by step because I think that's simpler. So we're gonna go start initialize. We get the context. We begin base with the base. The context has a base. This is the only thing that it's gonna have right now. 41. We'll return the context, and This is missing. Let me change that as well. Yeah, yeah. And I mean, and right now this is a little bit janky, but later we're gonna make the compression so that it works the same way. So mandatory prefix cby. So by count, it's 1. That makes sense. Well, the I base, it's 41, and the by count is 1. We got the table. Table has 1 bar of table, mother offset, blah blah blah. And this is the problem, isn't it? We don't have an entry index, and that's the reason why we have that context entry, which is invalid. So yeah, this is the janky thing that we got. That's erroneous because the way we are doing it is just wrong. Yeah, that's the caveat about offsetting. But yeah. So this is not correct. It's more like that. And and yeah, that makes this a little bit more complex, you know, in the sense that we have to keep track of the from the base part, you know, which in the first part we didn't care at all. We just, because we had flags and we didn't care of the past of the past you know. So probably, I mean, I don't know, if we see that this doesn't help, because we don't need to keep track of that, probably we don't need to keep track of the base, you know. We just have to continue along the thing. So I'll leave it like that. Yeah, because it's like, oh yeah, I have an offset, and then I have to think about this one. Uh, which in this case it's correct, but it's just hard to think about. And just having a pointer to it. Yep. So let's see now. So C by now we have an entry. What about the entry? It's a push, that's correct. We have our 12. Now C by is on a 50. That's correct. And here entry, it's a push as well. Now push REX, that's correct. I don't remember. Well, if I continue, by count it's 0. We are on the instruction. This is wrong, if you see here. So let me see. Let me compare the instruction string how now. R12, REX, SPL, REX, RBX, R13, REX times 2, 0, 0, 0, RBX, RBP plus REX times 2, yeah, RBX, RBP, REX times 1, FFFF, RBX, REX times 4, 0, 0, 3, 3, 2, 2, 2, 2, 1, 1, 0, RBP, RSP plus R12 times 8, 0, 0, 3, 2, 2, 2, 2, 1, 1, 0, R8, R12, R13 plus displacement. Then we have REX plus displacement, R8. Then we have RAT, RAX plus displacement. Then we have REX, RDX. Then we have REX, FFF0, OB. Then we have FED, ST0, ST1, that's incorrect. FOCOM, ST1, ST0. Then we have FLD, 00004. And VM resume, PLINR, XM0, XM108, shift left double, EX03. At EX00. So yeah, I mean that's correct. The only thing that's busted are the well, what can I say, the floating point instruction, so we can just change that as well. So, and yeah, we have an assertion because we haven't moved the offset because we didn't find an entry that was properly done. Well, actually, now I think about it, why did that happen? Since we should have a valid entry. Well, we don't. Well, yeah, we don't. Do we have a context entry? We don't have a valid entry. That's cool. Well, that's that's kind of weird, but that's cool. So let me stop here. So let me put here, where is it? What about that? I'm gonna put that. So I want to see what happens. There you go. This should already print everything. We haven't crashed at all. And I want to see what happens when we have an invalid entry, okay? So we're gonna say the ibase is to the ibase, you know, it's a pointer, it's a valid pointer. You know, it's just that it's null. And the value is null, okay? And then begin. There you go, mandatory, REX, get mnemonic. The count haven't changed at all, you know. So here we're gonna move by C by there. and it's like, oh, you know what's going on here. So we got the C by get table ID, and then get table ID gets us to it's an invalid because C by ID is an invalid. So whenever we get table ID, oh, because we changed this, isn't it? Well, this is not correct in that sense, because first byte can be null. So yeah, so let's change that. First byte, here we go. And it's more like this, sir, main of byte. So we print everything out, and then let's see what happens. We got a valid entry. It's a push thing. There you go, we have push rex, and we got to the right stopper. Push rex. And there you go. Okay, so there you go. That's our little change there. And I don't know, I mean, I don't know if that's gonna work, but we have to see. I like the semantic of begin and end. I mean, I think that I like that. But I mean, it was not like I was expecting more. I was trying to make something there more that was a little bit more understandable. But probably, I mean, it's not that it's hard to think about offsets. It's just that in the way that in the way it works, it's just that a pointer it's more useful in this case. Who knows? And one thing to think about is like in the thing we had before with the pointer, these calls here, where is it? The calls that now are dependent were independent in the past. So fetch fetch memory operand. These two, in the past I could just switch them and everything would be okay. Right now it's not, because we already modified this stuff. So if I do it this way instead, everything will be busted. Let's see. So if we come back here, yeah, we have CL, REX, we have a different idea of what's going on here. So XML1, yeah, so everything is kind of crazy there, and it's because of the way we're doing now stuff. So we should, I don't know, I mean, if we want that independence, we should go back to the pointer stuff, and we have, I mean, not necessarily a pointer, but we have to have two variables for that, you know. So yeah, I mean, we can add a variable that there so that you just don't modify the C byte, and we always keep the thing here. So we can even modify that right now, you know, and just say, hey, you know, and probably that's the problem with the st0 st1 thing. So the thing that we want is two pointers, two inside the context, two pointers, two counters, sorry. Right here, so that and that's the reason why it's not working the SIB. But one thing we can do is just to have a byte count, you know, a global byte count or instruction byte count, and a byte count, and operand byte count, you know, which is the same as, well, this is operand count and this is operand byte count, you know, and that's a little bit more that how we had it before, which is gonna just gives us to the past, you know. So instead of having or in fact we don't need that, we just need this. And I'm gonna use this with this to change this as well. So now let's change these two, and then we are gonna set up. Okay, so this is get REX fields. I can just then well, yeah, this is confusing. And this is the one that's gonna change. Now this is just gonna be this. Now well, we probably need the pointer to it. Yeah. Get mnemonic entry. change this to I by count. Then we change this as well. This is gonna be that's it. So now the only thing that we have to change is to set the mother and byte somewhere, so that we always have, we can have this switch, So if we do it on the memory, for example, we can even, we can do it on the mnemonic even. Like here we have context, mod RAM, equal context, I by can. You know what I mean? Do you know what I mean? And this is because context space IBs. There you go. And I think that's it, isn't it? Now on the fetch register operand, no, on the other, we get it from the mother and byte. So yeah, that's the only thing that we have to go, so that this is independent, and now we can just flip it around as we want. Well, what's going on? So let's see what happens now. There you go. Let's make the comparison. We still have the problem with the ST0 thing, so that seems that wasn't the problem. Where is the Win32 EagleFly? R12, REX, SPL, REX, RVX, R13, REX times 2, REX times 2, REX times 2, So yeah, everything seems fine. And just before solving the SD0, I just want to see if we have solved correctly for this. There you go. Yeah, well, now they are independent, so that's nice. RAX FFF0, yeah. So now let's solve for the SD0, SD1. Oh my god. Oh, let me close it. So I want to put a breakpoint there. I don't know what are the floating point instructions. They should be this string. So I'm gonna solve that as well. So whenever we are on there, we have already printed out all the stuff. Now we are missing the floating point instructions. So the C byte I base, it's D8, that's correct. We have REX percent, no. So we get the mnemonic, we get entry, we have the table. What about table? So the entry is, oh, look at this. Oh no, my bad. Now the entry is a fat, that's correct. So we don't have rec fields inside. So we just move around. And so why did I by count move? That's a little bit weird, think about it. Because we have I by count, if we have mother offset, then we'll get passed to the other instruction. So this is already busted. So the I by count is just the problem. So let me rewind. Boom. So we begin the context, you know, we have a context. Oh, we have a yeah, abide count is that. So abide count hasn't moved at all. It's just here where we have abide count. Oh, okay. So no, yeah, that's correct. Okay. So we gotta fetch memory operand. And then we can just say, well, you know, abide count. In fact, we can change this to mother m, and that would be the thing. You know, you don't care about nothing else. Well, what happened there? Do we have something? We have st0. Okay, I have to rewind a little bit. I have to rewind. Get mnemonic. Fetch memory operand. So yeah, we have to do that. We pass the flags, everything else is the same. Pass the context, so let's see what happens here. Register operand size is FDP. That means that we need the operand size of the thing. We gotta fetch register operand. With the operand size, it's blah. So we have FP, you know. And we're fetching the RM field. That means that we need the offset A, and we got the offset B. Alright, that's pretty straightforward. And then we make the offset selection. Oh, I see my problem. Yeah, we are doing the offset selection even though we shouldn't. You know, my bad. So we're doing this, and we're modifying the selection with the reg value, and that's not the thing that we want to do. That's not the thing at all. Fetch register operand. So here it's just this. My bad. There you go. And that's it. That's it. So we print that out, pretty straightforward. And now we see here, we get the mnemonic, we have our entry there, fat, there you go, fetch the memory, fetch a raster, and there you go, we have a selection, put your raster name, and the raster name has a context now, has a buffer that is st0, that's correct, result true, put your raster open, context result, there you go, up by count, there you go, we already moved the by count, that's okay, doesn't matter. Now we fetch the raster open, the same thing, and fetch raster open. Let's see what happens here. Selection offset, entry rect offset. Now fetch rm field, there you go, push it, we have st1, that's correct, and we print in the instruction, that's totally correct. There you go. And there you go, R12, REX, SPL, REX, let's just match it. R12, REX, SPL, REX, RBX, R13, REX, REX times 2, RBP, REX, RBX, RBP, REX times 1, RBX, REX times 4, blah blah blah, RSP, R12 times 8, RBP, R8, R12, R8, R13, R8, REX, RAT, REX, RAX, RDX, RAX, F0P, ST0, ST1, ST1, ST0, O4, FLD, BM resume, 018, AX03, and 0. Alright, so that's good, that's nice, and yeah, so I think I'm gonna stop here. But please, if you have any questions, post them on Twitter or YouTube, and I'll be there to answer. Please make your questions relative to the thing we did today. And yeah, with that said, I would say thank you very much for coming up onto this stream, and I will see you all on the next one. Take care.